Hello math fans, this is Miss Newell coming to you live with lesson 7-3 from page 119. Too much? Probably. Sorry. I'm not live anyway. By the time you see this, it's been pre-recorded. Well, I'm still alive, but the presentation's not live. You get what I mean. All right, on page 119, let's get started. Writing equations from verbal descriptions. So we've got two things we want to accomplish here. Today we want to be able to write a linear equation given a verbal description, and then we want to be able to graph and analyze functions on the same coordinate plane so that we can make comparisons of multiple functions at a time. So let's see what we got here. Suppose that the speed limit on all parts of the Interstate 20 has been changed to 70 miles per hour. Travis finds that he can now average between 50 miles per hour and 70 miles per hour on the trip between Pecos and Dallas. Write an equation that represents Travis's distance d from Dallas as a function of the hours h since he left Pecos if his average speed is 50 miles an hour. So remember that Pecos and Dallas are 450 miles apart. And we're writing an equation for d, our distance from Dallas. So our distance from Dallas, if we leave from Pecos, would be 450. And as we drive, we're getting closer and closer to Dallas. So not we, I mean, unless Travis picks us up. But anyway, his distance is going to go down by 50 miles each hour. So I'm going to say, as always, you should pause the mix and kind of try things one at a time on your own and then use my talk through to help you check it. Because now we're going to write an equation that expresses Travis's distance d from Dallas as a function of the hours h since he left Pecos if his average speed is 70 miles an hour. So same function but changing the speed. So his distance is going to start out being 450, but he's going to get closer and closer to Dallas. So his distance is going to go down by 70 miles each hour. So his distance away from Dallas is decreasing as he gets closer and closer to it. All right, so on the grid below, they want us to graph the two equations we found in parts A and B, and then describe how changing the coefficient of h in the equation affects the graph. So this one was negative 50, this one was negative 70. And then explain why that makes sense. So let's see. If we do the first equation, it starts at 450 and then it goes down by 50 every time. This isn't the most convenient scale they have here. This is going down by 90s, so these are going by 45s for heaven's sake. Let's see here, that'd be 225. And 40 would be 45 would be 315, and then 405. Good heavens. All right, so if we minus 50, we're going to be at 400, and then we'll be at 350, and then 300, and then 250, and then 200, and then 150, and then 100, and then 50, and then 0. So for the other equation, we're still starting at 450, but we're going down by 70. So that'll get me to 380. Let's see, this was 450, so this was 400, 370 would be a little lower, 380 I mean, a little lower. So, and then minus 70 would be 310, about here, and then minus 70. So just keep minusing 70 each time and you'll figure out where you need to go. Next one would be like 240, so probably about here, and then 170, and then 100, and then like 30, and then somewhere between 6 and 7 it's going to get to 0. So if I plug 7 in here, I would get 450 minus 7 70 times 7, which would be 490. So you can see that it's in the negative. So he gets there before 7 hours. So somewhere between 6 and 7 hours, he's going to be arriving in Dallas, because this is his distance from Dallas, coming closer and closer and closer down to 0. So describe how changing the coefficient of h affects the graph. So the coefficient makes line steeper as the negative number increases, meaning the number itself isn't increasing, but the negative, the 70 part of it, so it's more negative, so it's getting more steeply going down. And that makes sense because the coefficient of h is the slope, so it should affect steepness. So on the graph above, they want us to sketch the vertical line h equals 4. So h is hours down here along the bottom. This is our h-axis. So where h equals 4, here's the vertical line. And highlight the segment of that line that gives all the possible distances from Dallas 4 hours after Travis leaves Pecos. So that would be anything in here. Anything between here and here is the part where it's in between the two graphs. So that looks like it's between, and we can figure out exactly what that is. It's a little hard to see from the graph, but if we did, let's see, if there's a pen I can see better. H equals 450 minus 50 times 4. We would get 200, so H equals 450 minus 200 equals 250. And then if we use the other speed, 450 minus 70 times 4 would be 450 minus 280. So that's going to give us how far he'd be if he had been going 70 miles an hour, which means he'd be at like 170. So this right here is between 250 and 170. So he would be no more than 250 miles from Dallas, and it's going to be hard to see on here, and no less than 170 from Dallas. And write an inequality to represent that. Well, we're pretty good at writing an inequality, compound inequality, in the form of a conjunction, saying that all the values between and including 170 and 250. So the inequality we just wrote describes the possible distances after 4 hours of travel. The line segment we drew contains the set of ordered pairs h, d, so hours and distance pairs, where h equals 4. So in here, in this yellow part here, are a million trillion little solutions to h, d pairs that would make that true, because he can be going part of an hour and part of a mile. So there's all kinds of little distances in between there, and that's why we write it as an inequality like this, because we wouldn't be able to list all the possibilities. The value of d is between the values given in the inequality we wrote. For each value of f, a vertical line segment can be drawn to find a solution region for all possible distances h hours after Travis leaves. Since he could be going any speed between 50 and 70 miles an hour, right? And he might change, so it might not be the exact same speed the whole time. So there's lots of distances he could be after a certain time, but they'd always be between the paths of the 50 mile an hour trip and the 70 mile an hour trip. Shade the region of the graph for the ordered pairs HD such that H represents all of the possible times and D represents all the possible distances from Dallas after H hours of travel. So what we're looking at there is we'd be looking at all of the values in here. I wish I had a highlighter on here so I wouldn't have to green it out completely, but all of the values in between these two lines at any given hour, anything in there, anything in that green area would be a solution. There's a pair, an H comma D pair that would be one of the possible times and distances that he could be. So anywhere in that wedge between the two lines. And those lines should be continuous anyway. I could no sooner draw a straight line on this PowerPoint than fly to the moon, so I'm not going to try, but those lines could definitely, the red line could have been continuous and the blue line could have been continuous. I just didn't try to connect them and obliterate my graph. So Sumi and Jerome here start riding their bikes at the same time, traveling in the same direction on the same bike path. So they're both starting in the same place. And Sumi rides at a constant speed of 10 feet per second, and Jerome rides at a speed of 15 feet per second. And we're going to write an equation that expresses the distance d that Sumi has traveled. So Sumi's distance, this is for number 3, her distance would be, Sumi was going 10, so 10 feet per second. And she just started at 0. They just started in the same place, so there's nothing to add there. It's just 10 feet per second. Then Jerome's would be, for number 4, Jerome's distance would be 15 feet per second. Oops, don't know what happened there. I'll just leave it with a little tail on it. So then we're supposed to graph the equation. So take a minute and set up a graph. This is the scale I chose, going by singles on the seconds and going by tens on my distance in feet. So this will be my x-axis, this will be my y-axis. So go ahead and pause it and get your own graph set up if you haven't already. And then we're going to graph them. So let's see, maybe I'll make his be the blue line, so it kind of matches, but I'll make hers be the red line in case it doesn't show up. So she goes as 10 feet every 1 second, so 10, 20, 30, 40, 50, 60, and so on would be her line. And I'll do my best to draw this line straight, no guarantees here. Whoa, it's kind of tricky, whoa. Okay, pretty good. And then he goes 15 feet every second. So he'd go 15, 30, 45, 60, 75, 90, 105. And that would look kind of like this. Kind of tricky. All right, and then it says explain how to use your graph to find the distance between Sumi and Jerome. So number 6, after they've been riding for 5 seconds, how could we use the graph? Well, what we could do is we could draw a vertical line at 5 seconds and we could see how far apart these guys are, because Sumi is going 10 feet per second and Jerome is going 15 feet per second. So he, at that point, at 5 seconds, he's gone 75, and she's gone 50. So, and here's the words. You'll need this on your embedded assessment. So, the distance between them, maybe something like this. It doesn't have to be these exact words, but this will give you some words. The distance or the range between them can be seen where the vertical line at x equals 5, which stands for 5 seconds, intersects their two distance equations. So we can just look at the graph and see they're all right. They're between, she's at 50, he's at 75. So they are 25 feet apart. All right, now again, you should be able to do 7 through 12 here on your own as one big problem. So try that and then pause me and unpause me, and we'll see if I need to teach you anything or if you've got this. So let's see. We're going to graph the equations for 7 and 8 in the first quadrant of the same graph. First quadrant just means we're only using quadrant 1 over here in the graph because we only have positives. So we're not using quadrants 2, 3, or 4 right now. We only have positives. So the equations represent the height, y, in centimeters of Ellie's and James's model gliders after x seconds. So always, when you're creating your own graph, make sure you have labels on the units. So x is your time in seconds, and y is your height in centimeters. Now, when I set mine up, just because of the size of the graph I needed to fit on the screen here, I'm going by 2's on the x-axis and by 20's on the y. So the 20's on the y would have been really handy, especially if my time went by single seconds, but I'll have to think about this a little bit more. So Ellie's starting at 220, and she's going down 20 every second. But my seconds are in the cracks here. So there's 1 second and another 20 on 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7, 8, 9, 10, 11. Looks like she gets down, her glider gets down to the ground or a height of 0 after 11 seconds. So now your graph might be a little more flat, a little more spread out depending on your scale, right? So my scale is going by 2's on the x and 20's on the y. So that is Ellie. Let's see. So I'll just call, maybe I'll put E here for Ellie. And then the other one, James, he starts at 220 also, and he goes down 15 every second. So that means every 2 seconds he's going down 30. That might be an easier way for me to do it. So down 20, 30, 10, 20, 30, 30, 30, and 30. And it looks like he gets down, his is down sometime around, oops, what's that doing? Before 16 seconds, so maybe even 15 seconds, it looks like. Let's see here. Whoa. All right, not terrible, not terrible. So that's James. Okay, and then it says draw a vertical line segment that connects the graphs at x equals 5. So x equals 5 on mine is in between here, because 5 would be right in here. Interpret the meanings of, let's see, describe what segment the segment represents in words and with an inequality. All right, so for number 9, the line represents how much higher one is than the other, or how, let's say, instead of how, let's say, represents the difference between the heights of the gliders at 5 seconds. And then, let's see, end with an inequality. So let's see, I might need to use the equations to tell exactly what that is there. So after 5 seconds, this would be negative 20 times 5 plus 220. So that's negative 200. So that would be, and negative 100. So that would equal 120 for Ellie. And then his would be negative 15 times 5, which would be 75, negative 75, plus 220. So his is going to be at 145. So that's what this represents right here is 145. And this here is 120. So the inequality would be that the height is between 120 and 145 inclusive. Interpret the meanings of the coefficients of x and the constants in terms of the context. So both start at a height of 220 centimeters. That's the constant. And the Ellie's is descending at, let's see, 20 centimeters per second. And James is at 15 centimeters per second. So they're descending, and that's why their slopes are negative numbers. So descending 15 centimeters per second and descending 20 centimeters per second. Whose glider was in the air longer? James's was. Hopefully you came up with that because his took longer to get to 0, right? His took longer to land, longer for his height to get to 0. So there you go. Good job. So now you probably just want to go back and work through anything in these last few lessons that you think is a little bit iffy. And if you feel like you need extra practice on slopes or direct or indirect variation or anything from Unit 2, be sure you ask for that. If it's just figuring out the reasoning on word problems, the more time you spend just reading back over this stuff and practice interpreting those words, the better off you'll get. So always lean on me for help. I'm here for you.